Why should I like you? Denzel said. Why should I like you? What the law that make me like you? It's responsibility. It's my responsibility to do all my son. So the point is, you should be responsible. You should be a responsible man or girl or boy. Doesn't matter. Girl or woman doesn't matter. Sorry. So you need to be responsible in your life. Don't be like just a lazy, irresponsible one. He doesn't care. He doesn't care about everything. No, you should be responsible. You should take care of responsibility. Because now at this stage, you are at a time that you're building your attitude. You're building your personality. Trust me, if you don't do it now, at this time, you will never be able to. Because this place allows you to build your communication, to build your skills, to build your personality, your attitude, and to be a responsible one. Don't just, okay, take the lecture and just throw it. You don't need to be like that. Don't throw it. Once you finish the exam, don't throw it. Because that bad behavior, just keep it, save it, just for future. Because you remember this is your history. Because you remember one day in 5, 10, 15, 20, 30 years, remember, did both lectures I couldn't get in that day was this last year. Because this year, when you throw them, you are throwing over your history. That's bad, so bad. So it's not about paper, but it's about your history. So you remember that what you did at that time. So you need to be responsible, not to be lazy, like bad people. Please be silent. That's not good, like Russian. Good. See a Russian guy how they speak English? No. Yes.
Can you just did you mark me as my house?
What's the name?
Rania.
Rania. R-A-N-Y-A.
Yeah. Russian people, they are a bit funny when they speak English. And actually, they are also a bit funny. When you speak to someone from Russia, he just takes everything seriously. So you tell him, no, this is not right, this is incorrect, this is wrong. Why are you not saying wrong? Why are you saying wrong? Say, yeah, you've written that wrong, so you need to correct it. So I think this should be changed like this. He will just make it like a personal. And when you talk to him, you just feel someone will come to you and punch you in the face. Even you speak to him, with the phone or via Skype in a meeting online, you just feel, it just a hand comes with a bottle of vodka comes from the screen and punch you on your face. Those Russian. And they speak, yeah, it's good. Just like this. That's so crazy. Sometimes you feel they are lazy. Yeah, they are lazy a bit. Because they drink a lot of vodka. Anyway, sorry for this unplanned lesson. Anyway, we talked last week about a substitution reaction, and we saw how the reaction is funny and has some simple problems with variable or the chemical environment on the substrate or the nucleotide or the leaving group. So the reaction is very direct. Just a nucleophile attack an electrophile carbon. Someone leave. That's it. Very simple. But the problem with this reaction comes, comes from competition with elimination. So that's what we want to see here. Because elimination reactions, they are competitive to substitution. You are not controlling the reaction very well. Instead of having a substitution, nucleophilic substitution reaction, you will have elimination. Why? Because we said the nucleophile is base, so has a basic properties. Therefore, it's capable of doing two things rather than doing just one thing. So instead of attacking a carbon and just punch it and make someone leave, no. It's also capable of taking a proton from the next carbon, which is called carbon alpha, to the leaving group, and doing elimination. So therefore we need to just recognize So that's silent piece. Because that's kind of so therefore you need to be careful here. And also this lecture also will be kind of revision for the previous two lectures or previous lecture. Because you try to connect between the elimination and the substitution. Okay? So I wish you enjoy it and you understand it. And anyone has a question about everything, any question, just ask and don't be shy. Don't think that your colleague is smarter than you. Trust me, he also doesn't know how that happened, but he's also shy, he doesn't want to ask. So if you ask, they might not on you, but don't care about this. You just try to learn. And if you don't want to do that, do it another way. So write your question on the lecture, or write them in a text, or in a Word doc, or and send me an email, and I will answer all of your questions, or come to my office anytime. So I don't care. So as long as it's there, just come to work. So it doesn't matter if it's just office hours from 8 to 10 or not. So it's my responsibility to help you, but also it's your responsibility to be responsible, to go and read, take your part, because it's not only on me, it's also your responsibility to read, understand, search for the problem. Not every single time you just go to your lecturer and ask him, okay, Professor or Dr. Akil or Dr. X, Dr. Y, please explain this to me. You should go and read it online first, or read it over a book. Does that make you irresponsible? So why should I read it for you? Where is your responsibility in it? So you need to read, you need to help yourself. It's not because I don't want to do it, no. No, I would love to do it. I would love to help you. I would love to make you happy. When you make success, I feel it's my success. But if you don't want to help yourself to improve your skills, here, sorry, you're a bad one. So that's why sometimes you feel a lecturer doesn't give a lot of information. So he's not because he's stupid or he doesn't know. Sometimes he tries to deliver a message for you that you should take care of responsibility. You should be responsible and go and serve, because that's where you improve your skills. Because you need to learn how to solve a real problem, real life problem. So if you just keep depending on someone else, you will never learn. You need to solve things by yourself. That's how you develop your skills. Anyway, so in this simulation reaction, or this chapter, or this lecture, which we spend this week and the next week, so I try to make it clear as much as I can and simplify it as much as I can, which is not complicated, very simple. It's just a base, deprotonate a carbon, that's it, and leaving group going out, that's it. Very simple. It's like here. Elimination reaction, for example, let's say, okay, let's say here we have bromine. So we have a base. Okay, what's going to happen? So this structure, we have two possibilities of reaction. So it's either nucleophilic substitution, which is SN1, SN2, or we said it also last week. We said this will, deprotonate that and give you an alkene. Sorry, there is here. It's a hydrogen. Plus, Br minus, plus, base, which is like something like this. So this is elimination. So substitution, you know it. So that will attack here, this will leave. So this is the elimination. So, and there is two possibilities of elimination, which is beta elimination and alpha elimination. We'll see it just now. But I'll focus on beta elimination. And that beta elimination, undergoes either via E1 mechanism or E2 mechanism, like SN1 and SN2. The same thing. So we will look at the structure and check. Is it, for example, E1 mechanism or is it E2? So normally the same behavior like substitution reaction. So let's start with this general reaction. You see in the picture here. This is just explain the whole chapter. So you just explain you have a base. So that base will deprotonate this, this carbon called carbon alpha to this carbon. Because this carbon carries the leaving group. So this carbon number 1 for the leaving group. So this carbon number 2 for the leaving group. So we say this is alpha, and if there's another carbon, we got carbon beta, like that. Okay? But because the bromine is located on the carbon alpha here, so this will be carbon beta, like carbon number 2. So that's why they said beta elimination, because elimination doesn't happen on the carbon number 1 here, so it's on the alpha here. Okay, because you don't want to get confused between carbon in group, for example, here and here. So here carbon in here, this is the carbon here, okay? This is called carbon alpha. Why it's alpha? Meaning number 1 to the functional group. This is the function group. So don't mix up between this and this. Here the function group actually it's not like there. Here we have a leaving group. So this leaving group is actually located on the carbon here. And this carbon alpha, and therefore this carbon beta. That's why they say beta elimination. That means we are taking a proton from the carbon, beta, which is this one, exactly, which is here. This carbon beta. So we take a proton from here, so we say beta elimination. So is there alpha elimination? Yes, there is alpha elimination, but it's limited to, to the structure, as you see here in our strategy. So this example here, or here, this slide shows you exactly what's different between substitution and elimination. So if you see here, this is this carbon here, this molecule, so it's attacked by a nucleophile like this. So and give you a substitution reaction. Whereas here, you see the same nucleophile. It could also attack here on this carbon and do substitution, but it prefers the elimination due to some structure problem here because it's crowded here. So it's not easy to come and attack. So when a deprotonated this proton, you will get an alkene. So the normal product for beta elimination is make alkene, or sometimes make alkyne. But most of the example we are using is our alkene. So we are making alkene all the time. You see here. There's no inversion of configuration here. We don't have it. Why we don't have it? Because there is no tertiary carbon. We don't care about the chemistry of the carbon that we are deprotonating there. But we care about actually the configuration of the alkene, whether it's cis or trans. So we have kind of problem here. But not like substitution reactions where we care about the molecule is chiral, okay? With it's chiral like S, in SN2 reactions will become R. Whereas in SN1 reaction, if it's S, then you will get 50% of SNR. Here, we are making alkene, so we are not making, quaternary carbon. We are not making a carbon with 4 single bonds have different substituent on them. So no, we are making alkene, which is, unsaturated group like here or here. So this alkene we should take care about it. So whether it's cis or trans. And this example would be definitely cis because it's not possible because it's cyclic. But when we have it like an open chain, like a chain of carbon, we will have a problem kind of, we are getting trans or cis. We'll talk about this later. Anyway, let's start with the general idea. So what is substitute, what is the elimination reaction? So elimination reaction, as you saw that example or previous examples, it doesn't matter. So we are just removing a proton, and leaving group, removed. Whereas in substitution, we are, attacking a carbon and leaving group, go out. So good leaving group here, to make a elimination so good leaving group, you need the leaving group to be, good one. The same as in substitution reaction, where we saw there in substitution reaction, we saw that the iodine is better than the chlorine, and the chlorine better than, iodine better than bromine, and bromine better than the iodine, the chlorine, and the chlorine is better than chlorine. The same thing here also. We want to make sure that the leaving group is good enough. But more interesting in elimination reaction, they prefer also not only the size. They don't only prefer the iodine and bromine. No, they prefer also a big molecule leaves. Like tosylated group here. So it's written here OTS, OMS, OBS. What does that mean? What does this? These are just abbreviation for a leaving group. So if you want to search for them online, just write, for example, OMS chemical, you will see the structure. Or OTS chemical, you see the structure. OBS, very, very big one. So, for example, OTS, here, that means this is tosylate group, means tosylate. Okay? This looks like this. Tosylate, it's like this. So, aromatic ring here, para, methyl, tosylate. So, sulfonic acid. Here. So this is a tosylated group. This tosylated group is a good leaving group. So when you attach it, for example, to a carbon, let's say to this one, okay. So deprotonation will happen here and make double bond, and this will leave. And this is a very good leaving group. So good one, really, really good one. Why? Because it makes very stable, anion. And that anion formed from the elimination is going to be stabilized by the structure here, because we have carbon in the group. So when you remove it, you will get this. When you remove it from the molecule, you get this tosylate ion. And this tosylate ion is stabilized by the next atoms, which are here carbonyl, here sulfonyl, here S double bond, or here S double bond, and also it's substituted by this aromatic ring here. So the ring and the double bond here is actually stabilize the anion formed in the reactions. Also like OMS. OMS means mesylate. OMS means mesylate, which is quite similar to this, but instead of having this aromatic ring, we have methyl group. So, OMS, methyl, or mesylate groups, or mesylates, like tosylates. Mesylate group. So this is also a good leaving group, but not like this. This is better because of the ring here, but it's also a really good group. It's so good. But this one is better by far. And the OBS, which is, oh my god, para-perfluorous non-exobenzene. So just so big. This is just big. I mean, you are not required to to memorize them, by the way. You just need to know how they look like, just to see them. So we have another one here. I'm going to throw it for you. You see how big it is. These silent. What was the problem? That's not good. That's irrespective. Something like this. I don't remember here. That's something like this. You thought I have it here. So see, this is OPS, which is all the parts are part of perfluorous oxybenzene sulfonate. It's a nice name. So this is, this is better by far than this one because it's so big, very big, and has a lot of, lots of driving rules. So it makes the anion form in the elimination better by far. Okay? So we said this, okay? So the presence of a good group is a prerequisite in most image reactions. So we said it, so we did good group. And okay, based on the deprotonation position, we have either alpha animation or beta animation. Our focus is on beta animation, but it's good to mention the alpha animation. So you see here, alpha animation is very simple. There's no complication. You are always making carbene. What is carbene? Carbene, it's a carbon with 2 electrons, located on the carbon. So we see here, for example, if you start with bromoform, like chloroform. Have you heard about the chloroform? Chloroform, which they, use it to inhale something. When you inhale it, they use it actually in animal houses to inhale animals to make it like a slave, like inhalation. So it's not. So be careful with it. It's dangerous, and it's ozone destructor. So it destructs the ozone because it generates chlorine radical. That chlorine radical will react with the ozone and then increase the ozone hole. We don't need more water because our water is already broken. So bromoform like this, when you expose this molecule into, for example, base like KOH, what's going to happen? So it will deprotonate the proton. We'll take that proton, and that proton, that deprotonation called, alpha, alpha elimination or alpha deprotonation, because we are actually deprotonating, on the same carbon that carries the leading group. So we say it's alpha elimination. So, because here, we said it just a minute ago, we said that, for example, okay, so this is carbon alpha, this is carbon beta. So in alpha elimination, you are actually removing the proton from this carbon, and you are generating actually carbene. You see it. So whereas you remove from here, you get a beta elimination. So alpha elimination is very rare, not a lot, and it's specific to some molecules, not always, not easy. So once you remove the proton, you are generating actually an anion. So, okay? So then this anion, which is this one, the same structure. So it will remove the get rid of bromide ion and make a sorry, not that. I hear CBr2, sorry. Please correct it in your lecture. This is CBr2 because dibromo carbene. I think I drew it wrongly yesterday. I'll try. It's written there, it's correct. Yeah, because yesterday I drew it in a chemistry program and I put it wrong. So it's already correct in your lecture. So dibromo carbene. Where is the carbene? Dibromo because there are 2 brom on the carbon, but because the carbon here become like carries, lone pair on the p orbital. So those lone pair on the carbon called carbene. They are not stable molecule. They form, and need to be, kept very safely because they are not stable. Because normally carbon prefer, 4 equivalent bonds, so to make 4 bonds, not 2 bonds. So when it carries 2 electrons on it, so it's a carbene. So carbene chemistry is very well known chemistry, carbene. So we use a lot of methods to do some reactions, recycling or stabilization. We use a lot in pharmaceutical industry to make a reaction. Okay, so this is alpha animation. So even the next example with dichloro will be the same. So here example, this is chloroform, the one I told you about. This is chloroform, so the base will remove that proton and make, and then so once it removes it, so let me drop it here, make it more clear. So we have here OH. So this is the mechanism, very simple one. So the OH will be what they take that proton, and that up here, this leaf. Okay? So it will be like this. This proton and this bond, will be on the carbon, and the carbon will lose chloride ion. So therefore it will make carbene, dichlorocarbene. Okay? So this is the problem, this is the mechanism. So you can actually draw it like in 2 steps, like the previous example, or you want to draw it like in one simple drawing. So this is here, we draw it just in 2 steps. We make the anion, and then, carbon ion, and then we make the multiplication. So that's carbon ion, so anion, because it carries negative charge. Or you want to draw it like there, it's up to you. But you need to show to move the arrow correctly. So, anyway, I hope that's a good introduction for the elimination. So let's go to the important one, which is the beta elimination. This is our topic for this lecture and the next lecture. Oh, sorry, yes. It's not real, I'm sorry. I'm just addicted to the deal. Yeah, here. So here we see it. Okay? So now, what's beta elimination? Just very simple, we said it. We are actually taking a proton from the beta carbon. So the carbon next to the carbon that carries the leaving group. That's very simple. That's the reaction. This reaction happens in 2 mechanisms. The first mechanism is E1, which is unimolecular reactions, or E2 is bimolecular reactions, like SN1, SN2. It's simple. So see here in this picture, it's just repetition actually. So this proton is located on carbon beta, this is carbon alpha that carries the leaving group. This is the leaving group. This carbon beta, will give its proton. Doesn't, so the base here, be careful, the base here doesn't take hydrogen atom. You need to recognize between hydrogen and the proton. What's the difference between hydrogen and proton? What's the difference between, H as a hydrogen atom and H with plus? Sorry? So what was the difference? Why we say this is proton, we say this is hydrogen atom. And we said here the base take a proton, doesn't take hydrogen atom.
Proton has no electrons left on the
So
orbital.
it's empty orbital.
Yes.
So the base takes the proton only, the empty orbital hydrogen. Empty orbital hydrogen. I'm charting. So I'm just seeing some, I hear you're going well. You don't need to chat, please. If you have a question, just ask. Please interrupt me. Okay, so the base take the proton first. So it doesn't take hydrogen. So that means this bond, which made from 1 electron from the carbon, 1 electron from the hydrogen. So those 2 electrons here, this bond, will be, kept for the molecule. So the base, it doesn't take any electron from here. Just take the empty orbital. The empty orbital of the hydrogen, which is named by proton. Why? Who knows why? Why the base here takes the proton? Why the base here takes the H plus or proton or H. Why it take, why it does remove this, this atom, or why it should remove? What is the problem? What does do?
Because both of them have negative charge. The electron and the
No, actually. We just said it. We said the proton. Anytime we say the proton. So,
Because proton is active for elimination.
so why it's active? Why it does take the proton? What's the problem with this atom? What's the problem with this atom?
because it needs to be in equilibrium to stay like
Because proton
Because
wants,
it needs to be stable. Like stabilization.
No.
the proton wants to fulfill the electrons on its orbital, and the oxygen will give one electron.
Very simple. Just said it.
And one is-
Yeah.
It's the best property to be accepted.
Yeah, quite close. Yeah, quite close, but not quite correct, but quite close. So the role of Bayes, what they took, according to Bronsted Bayes, what they do, they accepted proton. They took proton from the molecule. So that means that proton is acidic. So it's acidic proton. Acidic, just remember this word, acidic proton. You need to keep this word in your mind for the next lectures. Because we will talk a lot about acidic protons. This is our target, where for the alpha substitution, nucleophilic acid substitution or addition reactions or whatever. So this proton here, this hydrogen in general, we said it's a proton. So the base take the proton. That means this hydrogen is already acidic. That means it's Bronsted acid, so it gives a proton. So because this proton is acidic, so the base will take it. Why the base doesn't take, for example, let me remove here, the gamma proton, let's say, So, this is alpha, this is beta, this is gamma. Okay? Okay. The base, when you have base, what's going to happen? It's either take the alpha proton, beta, or the gamma. So, which one is the most favorable one? Is the beta one or the alpha? The gamma is totally no, doesn't work because it's not acidic. And even if the base approach on this proton, no living group next to it to make a stable functioning state. You'll see that. So the proton here on beta, it's acidic, and also when we remove it, we are actually making stable functioning state and get a double bond, which is strong bond. At the same time, we remove this leaf. So there's an antiplanar geometry, we will see in a second. So I want to say, the base when it comes here, it's going to deprotonate this proton because it's acidic. Okay? It doesn't deprotonate this proton because it's not acidic. And also, not only not acidic, there is no actually leaving group next to the carbon here to make a double bond. So that proton is acidic, therefore it's possible to take it by a base. And also, the other reason is that when you get this proton, you will form a double bond which is very stable in the tri-state. We'll see the tri-state in a second. So we'll explain these things here. Okay? Elimination on reaction which a small molecule. So HCl, HBr, H2O is eliminated. So what does it mean that? So then we are actually taking the proton from here, and we're taking it from, for example, here, or chlor. So in general, we are removing HCl or HBr because we are taking a proton from here, and its counter ion here, which is called an ion. So positive charge from here, which is the proton, and negative charge on bromine, which is the bromine. So we are taking actually HCl or HBr or whatever. So that one doesn't make sense. So now, in beta emission, we have two kind of mechanisms, E2 and E1. E2, it is bimolecular reaction, like SN2. Exactly. So the rate of equation depends on the concentration of the nucleophile or the base, let's say here, the base and the substrate. Whereas in E1, it just depends on the, on the substrate. Exactly the same on the SN1, SN2. See here, it's bimolecular, and the rate constant depends on the rate of reaction depends on the concentration of the substrate and concentration of the base. And here we said base or nucleophile because both of them behave similarly. Whereas in E1, no, it depends only on the concentration of, a substrate. But there is a one word here. Just read it. Concentrated break. And we said here, break bond, then make a pi bond. There, concentrated break, make bond. You remember? We said last week in SN2 reaction, we said it's a concerted mechanism. So the reaction happens in one single step mechanism. Once the nucleophile approaches the carbon and you remove leaves. So all of that happened in one single step in the SN2 reaction. The same thing here happened also in E2 reaction. In one single step. So, like when we draw it here many times, we said the base here will take that proton, and this comes here, and this leaving. This is, do you see this arrow? This attack here, and this one comes here, and this leaving. This is all in one single step. This is what called A2 reaction. However, E1 reaction, like SN1, is not concerted. It's two-step. The first step in SN1 reaction, you remember, the dissociation has to happen and get a carbocation, and then substitution. The same thing here. Dissociation has to happen for the tertiary structures, and the elimination happen after. So the same behavior. Okay? Anyone just confused about SN1, SN2 with E1, E2? They both behave similar. Rather than we have their substitution, we have here elimination. So just connect both. They are both the same. In SN2 reaction, we have a concerted mechanism. At the same time, the nucleophile approaches the carbon, leaving group leaves. The same thing here in E2 reactions. At the same time, the base approaches the beta proton here, leaving group leaves. The same thing. In E2 and E1 reaction, similar to SN1. SN1, the nucleophile doesn't approach the molecule. No, first we need dissociation to get a carbocation, and then the carbocation is attacked by the nucleophile. Here the same thing. So the base doesn't approach the molecule. No, first we need to have the dissociation, and then the elimination will happen. So the same behavior. And both of them are bimolecular in E2, SN2, and unimolecular in E1 and SN1. Any question? You're all smart. Are you good with that? Please ask us if you don't understand me, just say it. Trying to sacrifice, you know what I finished my lecture with you? I got so tired. I just want to sit. Because I tried to sacrifice in order to deliver the good knowledge, good information. To explain everything. I'm not leaving anything on you, just something, give it all of you. However, I should leave something for you. But you are lucky. So, let's take an example on the beta elimination, which is the E2 reaction. Which is the E2 is similar to SN2. Similar. See here, the mechanism. See here? So this is the base. you know, take the proton on the carbon beta, because this is carbon alpha to the leading group, carbon number 1 to the leading group, this is carbon number 2 to the leading group, and which is called beta, so it's beta energy. So once this is come to take that proton, so this will come here, make a double bond, that lead. And all of that happen in one single step, silence. Why not just keep, chatting? If you have problems or you have a question, just ask. Because that's not good. Next time, I'm going to deal with you differently because I try to be, very good with you, but unfortunately you're always breaking the rules. So it's not polite behavior. Impolite behavior. Speak and chat where your professor is just talking. You need to take an excuse from the professor and tell him I want to say something. Or I want to do something. Because it's totally different. Totally different. Just imagine if you are just talking to your friend and your friend doesn't care about it. He just keep watching his video. How angry you will be. You will feel that this guy, he doesn't care about you, he's not listening. He just keep, ignoring you totally. That means he's not interested in you. So that's what you're doing now. Talking, explaining you are not interested. Just keep talking or chatting with your next friend or laughing. However, I can change my behavior with you and be very, very tough. Okay? When it comes out, then you will be angry. Then you will go and complain against me. But trust me, that's not going to change anything for me. And they are not able to change my behavior. Because I'm the guy who's, controlling totally over the class. And I'm responsible for you in this material. So no one is able to affect on my decisions. Now remember, this university, they give us the 200% freedom to control the class. It's not like other university where a president or the chair interfere with the decision of the lecture. No, we have the freedom. And you saw that in this university it's not easy. You need to provide, a good level, a good English language. So that means you are actually, prepared to be here. So therefore you are spending money and time. You need to use that time and money. When I go to Southampton, this is my base here, I used every single second there for research, understanding, saving information, writing. Every week I work 7 days per week in the lab, from the morning till 8, till 10, every day. This is my opportunity. I should take it, this chance. This is my chance, this is my shot to take it. Because I spent a lot of money, like a $250,000, It's not something simple. So when you pay like a tuition fees per year, $30,000 for the university, and you spend all yourself, also $30,000 per year, that means $60,000 per year, the cost. So $60,000, that means $90 million per year. 4 years, just count it. I get 300 and something. So therefore, you need to, use every single thing. You need to steal every single information. You need to learn everything because you don't have the chance again. The same thing here. You are spending money, wasting time. You need to learn. That's your job. Otherwise, you are just wasting your money and wasting your time, and actually make your lecturer angry. So, because our job here, me and you and everyone in this city, it's like kind of complementary. We are actually completing each other. So if I don't do my job well, you will not do your job well. Your father will not do your job well. So every one of us actually completing each other. So when you go to a doctor for checking something, or go to an industry, or go to fix your car, so you need to make sure that guy fixing your car very well. If he doesn't do it, then there's something problem with him. And who make him to be a problematic for you? Trust me, someone else. And that someone else may be your father, or your brother, or your sister, because she doesn't teach you well, or she didn't, learn how to do that right. So the job is actually, we are actually working all together. So therefore, if I don't do my job well, you will not do your job well. Your brother will not do it well. So in the end, we are destroying the society. So the job, we should take care of all of us. The responsibility is on all of us. So if you come to the university and you don't care, what you're doing here and why you are doing here, actually why you are here. If you don't know all of this, positive, you don't know why you are here, why you're studying. What's the point? Just taking a certificate? Trust me, don't come here, go to Russia or India. Without going there, they give you a certificate with a few million IQ. Sorry for this. Yeah, so I'm trying to give you a few lessons from my experience. I'm not a big one, I'm still very young, I'm just 35. So, but I have really good experience. I used to be very responsible since I was like 6 or 7 years old. So that's what I'm trying to do from my experience, to be responsible. Because every one of you is able to go out and prosperous. Oh, you want to be failure? Don't be failure. Just drink and just eat and go to the toilet. That's your role. But you are useless for the society. So you will be active and useful. Anyway, so LS, for example, base will take that and they get out. So we said this is, we have here, what we have here, we have alpha and beta, yeah, the same that we explained. Now this is the beta carbon, this is the alpha carbon. So when the base comes, so it will take the beta carbon, take the proton from the beta carbon, not the alpha carbon. Why? Anyone knows why? Why? Why we don't have a deprotonation from the alpha carbon, not the beta. So need to answer this.
Only one hydrogen left.
So when you move from here, because it's SN2 reaction, so it's concerted. So what you're going to make? You're going to make a carbon anion, like an alpha elevation, and then you get a carbene. Is not favorable of these molecules. Because the carbon anion here is not stable. Because once you deprotonate alpha, so the brom will leave, so actually you're making a non stable carbon. Not like the others with the 2Cl or 2Pr. Because those 2Pr, they are, they will stabilize the carbon because they are rich electron atoms. Whereas here, no. And also, it's the transition state. So we need to think about transition. Let's see the transition state. Before we go to this, let's see the transition state here. It has two reactions, because you can see. So here, when we take a proton from here, so the transition state will be that kind of level. So that like 180 degrees between the leaving group and the deprotonation. What does it mean now? Let me explain it. So you see here, the base is actually, on the opposite side, like a trans. You remember trans? So it's opposite to the leaving group. And the degree here is kind of, opposite, completely opposite one, like 180. So on the transit state, what's going to happen? You are going to make a kind of resonance or stable transit state. It's like this. So this is the transit state, where we put double target on it, means transit state. So you see, on the transit state, this is how it looks like. So if you go and calculate this one using computer with a program, you will get that transit state. And this transit state, look, one leaving group is opposite totally to the, to the base. They look like 180 degree antiperpendicular to each other. So this one, so they are actually, every group is actually far away from each other. Therefore, there's no repulsion. They are like kind of relaxed geometry. very relaxed. No one touching each other. So very nice. There's no, interaction between the base and the organ here. It's very nice. The space is enough. But once we, minimize the space, make it very small, therefore it would be crowded. And then some problem would happen. We'll see that like in SN2. The same thing also here. So in SN2 and in E2, the same thing, the same factor that we talked about last week about the factor controlling the SN2 reaction, which is the substrate structure and the leaving group and the nucleophile. The same thing here. The same thing also. The leaving group, the structure, and the base. They all have the same problem because the base is nucleophile. We said that. So for example here, the same as in SN2, so the iodine would be better leaving group. The same thing in SN2. The bromine would be better than the chloride better than the chloride. The chloride is so, inactive, so actually inert. So it's not reactive in both in E2 and SN2. Yes. So this is just kind of, just what we said. So iodine is better than the bromine, bromine better than the chloride, so kind of repetition. So here here's the opposite. So when we talked about the structure, and the structure is a bit, opposite. Here we have one difference. So we see the structure and the E2 reaction. So the reactivity actually going from primary to the tertiary. And we will explain why. So in the E2 reaction, in the elimination, the primary is less reactive than the secondary, and the secondary is less reactive than the tertiary. I mean, the tertiary in the E2 is more favorable, whereas primary in the SN2 is the favorable one. And this picture explains, what you need. In the SN2 reaction, primary is more active than secondary, secondary is more active than tertiary. So I think that is very clear for you. There is no problem with it. Then why is that? It's a transit state problem. Transit state problem. So if you draw transit state between in SN2 reaction and E2 reaction, you will see the difference. So you will see the difference. You will see. Because we drew it last time with the SN2. And we saw why primary is more favorable than secondary, and the secondary was favorable than tertiary. So here, the regioselectivity problem and E2 reactions. Regioselectivity. What does it mean, regioselectivity? It means that we have a leaving group, on a carbon, for example, alpha, but there is 2 carbon beta next to the carbon alpha. That means the, deprotonation can happen on, 2 positions, like here, and this 2 bromobutane. You see here, this is the carbon alpha. We have here carbon beta. We have here also carbon beta next to the carbon base. So that means the protonation can happen either on here, this carbon, or on this carbon. Okay? So if it happens on this carbon, so that means we are deprotonating that proton and making a double bond here between this carbon and here, like here, to butene. But if the deprotonation happens on this carbon, terminal one, the terminal beta carbon, so we are actually making a terminal alkene, which is 1-butene. You can see here 20% yield, whereas this one is 80%. So what's the difference? Why this is 20%, the 1-butene, and that one is 80%? Look to the transit state here. On the 1-butene for the 2-butene. So this is the transit state. So look here, the transit state on the 1-butene here, this is stable, okay, leading to, this is stable. Because it's less stable, so you get less percent of yield. But you see here, we are making actually a double bond on the terminal position. So double bond is here on the terminal position, whereas double bond here on the, in the middle kind of getting support from groups from here and group from here. That means the group on the double bond from here and here, they are big. They are bulky groups. Where here, the groups are smaller groups, because here becomes just CH2, just hydrogen. There is no CH3 or something like that. So therefore, this one, so it will make, make the transit state, least stable, not 100% antiplanar, okay? So the reaction will happen, okay, but not majorly. So it will be like a minor product, and this is the major. So we'll talk about the E and Z. What does it mean? So, whereas here, it's more stable, so give you the more, more yield with major. Because on the trident state, which is 100% antiplanar, so they are anti to each other, like trans. So the carbon here, the double bond you're making here, actually, or let's say, the resonance structure on the transit state here, this is dotted line, actually is more stabilized because of the R groups here. Here, the R groups, just from one side, they are big, but from the other side here, it's just hydrogen, so it's not supported. Whereas here, the R groups, they are big enough, to support and stabilize the transient state. It's all about stabilizing the transient state. So, transient state, we said, what does it mean last week? We said
before the reaction.
so the state that connect the reactant and the product.
Before consuming the reaction.
Okay. What time is it now? 10? Oh, you want to take rest or you want to continue? Just leave early? Leave early? Oh, okay. Good. Anyway. So why I said it's actually written on the lecture. So on the trident state, this is more substituted here on both, here least substituted. Therefore, according to this, we can make a rule. So where should we take the proton from? Which position? We have like this one. You have a proton like this, and you don't know, where the people is going to take it. Where? Is it on this carbon or on this carbon? Here we just remember a rule called resistance flow. So this rule means we take the proton from the carbon that least hydrogen. So like here. So this carbon and this carbon. Which one carries more hydrogen? Which carbon? The middle or the terminal? Which one? Terminal carries more hydrogen. That means it's less favorable to give the proton. Because it's terminal. So that means carries 3 hydrogen because it's full saturation. So sorry, it's full of hydrogen. Whereas this one carries 2 hydrogen. So the rule is what I said here. So it's more favorable to take the proton or take hydrogen or take a proton, more accurate, from the carbon that carries lower number of hydrogen. So this carbon is favorable to give the proton than this, according to the rule, which is Zestiv rule. This is like a terrible name. Zestiv rule. Terrible. Okay, so it's a just rule, which is very simple. We just say it name. So if you have here this one, so this is the living group. So we have here lots of group can take proton. We can take proton from here, or from here. So from here or here will be the same because they are, equivalent to each other as symbols. Okay. So, or we can take from here. So we have three positions, 1, 2, 3. Which one is more favorable? 1, 2, 3? 1. So one more favorable because it carries less number of hydrogen, according to Zaitsev rule. It's a terrible name. Who gives you that name? Okay? So, but that doesn't mean that no product gonna, have it on this carbon. There will be some product at 10 or 15 or 5%, but it's minor. But that minor is so terrible because it's not easy to isolate it from the major. Oh, this is where organic chemistry is terrible. When you make compound and you have a problem like this, oh my God, how could you purify them? It's so disgusting because they are so close to each other and they have, they are quite close in, physical properties. The same quite close boiling point, quite close melting point. They are quite close when you put them in a column, they come quite close to each other. So, the separation will be disgusting because they are quite similar. Because maybe both of them are the same color, so it's not easy. So this is a problem. Therefore, when you do a reaction, make sure it's selective, very selective. This is what's called regioselectivity. Regioselectivity means that you have, one position and another position competing in reaction. So when the nucleophile comes, for example, take the proton, so it will have two options. Okay, shall I go from here or go from here? I don't know. Who decided that? It's like when you come on a road and you have, I got the version, I'm forking the road. Okay, fork. So say, okay, where should I go? Is it from here or from here? I don't know. So it's the same. So when the base approaches the molecule, will have the same thinking. Oh, shall I take this proton or this proton? The same. The molecule behaves like a human. The molecule has a brain. Trust me, because we are made from molecules, so we'll be similar. We are just, a mass of electrons and protons, neutrons, some positrons inside. So the molecule, so based on its approach to the substrate, it will do the same thing. And that thing called regioselectivity. That means selectivity on the position, or either on this carbon or on this carbon. So a selectivity on a position. So it's called regioselectivity, meaning from region. Regio from region. Okay? Regioselectivity. So which region should I take the proton from this region or from here? From here or from here? So there will be some kind of confusion for the base. But we'll make the most stable prime state will be the predominant approach. So this is the first example. Second example, two alkali substituents. So here we have, not like here, they have the three substituents on the carbon. So, this will be predominant. And we have this one here, and we have here also. And also here and here, quite similar. So where the proton going to be taken from? From this carbon, number 1, for example, just say number 1. This carbon or this carbon? The terminal one or the middle one? Middle one, because it carries the lowest number of hydrogen, according to this guy. Okay? Zaitsev. Should be Russian. Good. they say like this. Good. Yeah, I met a few Russian people in the UK. They still have also three friends from Russia. When I chat with them about the problem and research, they just take it seriously. Actually, you can't give even your opinion. They can't accept the opinion. Yesterday, we got a rejection for a paper. We sent the paper to a journal, an American journal, and then we got a rejection, just even without reviewing. Just in a week, we got an email. Sorry, we regret to inform you that we are not able to accept your paper. I said, okay, I know that. By myself, yeah, I know it. Because I told him, the paper is written rubbish. There is a good result, but it's not written well. It's not shaped very well. From the beginning, I told him, change these and these. This table should be figures. This one speech should be a table. And this one should be written like this. And he saw my result. I give him my part, so he asked me about something about mechanism reaction. So I solved it, and I computed for him. So I did everything, and I wrote in a very nice way, very pretty, with a lot of nice, pictures and figures. And he doesn't look to my result. Please see how I organize my work or my parts. He just doesn't listen. So we got the rejection yesterday. I tried to give him an advice, and yeah, unfortunately that happens. I didn't expect that. However, I really expected that because I don't want to make fight here. Because you can't discuss and negotiate things with Russian people. That's the problem. Because they drink a lot of vodka. That's the problem. They drink vodka even in the morning. And they when you say, why drink vodka? They say, yeah, it's good, good. In the morning, good, good. This is what they say. Yeah, it's good, good. What's the good thing from the morning? Go and have breakfast and get tea or coffee. So here, we don't have any options. We don't have any options. So it's only one option. So the bottom will take from here, you get this terminal alkene. So there's no option. Sometimes they are so lazy because of the ball. Yeah, they're really lazy. They are putting guns. They make guns. They are interested in war in their guns. I know it. And they are really interested, in chemistry. If you go to Russia and check Russian universities, and go to the chemistry of the bottom of chemistry, you'll see all they interest is in nitrogen chemistry. They love nitrogen molecule. So the molecule that carries nitrogen, like amines and things like this. Because those molecules are useful for things like this, for exploding things. So then imagine the paper is coming from someone from Iraq and someone from Russia. How could be accepted? This is terrible. Because I told my friend Sammy, he's in France, yesterday, he said, Sammy, that could be solve this problem. He said, imagine you are from Iraq and he's from Russia, and you are talking about nitrogen chemistry. They will never accept it. So it's kind of a problem. Oh my God. Okay. This is wrong. So here, example, this is just repetition. So the slide is just the same rule. So we have here wrong. So same rule, we said it. So the bottom will be brought to this we're making a good job last week, next week on the Russian. See that you are interested in Russian. Is there Russian? Someone's relative. Please don't take it personally. Yeah. Yeah, and Russian like this, yeah. They are so, they think they are seriously. Americans, by the way, they don't take it seriously. They don't take it seriously. I'm not like this. British, they are very formal. They are problem. Morning. They give you yellow smile. That means they are lying. That's yellow smile. But they are very formal, very polite. If you live with them, they're, for 1 or 2 years, you just get adapted to the situation because they are very polite. They love to say, thank you, yeah, thank you very much. 3 things you need to take care of when you go to UK. Thank you, and smile, and take the cue. That's the things, you need to do it. So when you see cue, you have to, wait, don't go and jump like here. We just jump like you go there. There you should take it, because everyone was shouting at you. Don't do that again. That's not loud. And that, and if someone from countryside, they speak like very informal language, like why you do that? They just, they're just telling their tongue or their mouth and say in a way, make it very funny. You see some films for Shelby or and Kirikimba? You see the accent? Imagine someone talking with you like this. You would never understand it. Even the British don't understand it. So see here this example, yes. Next week we'll bring in an example about Russians. They are funny. Anyway, so here we have get carbon and gold, so the reactions will, will be one product. Sit out, please, guys. Sit out, please. So here we have a molecule where there are two beta carbons, but they are equivalents, It's equivalent carbons. So we draw a line here, or we put that in here, it will be the same. So the same. So one single product. There's no another product. It's a simple molecule. This is the rule. So here the same example we said it. So we have like here, for example, bag like this with 70%, where the importation happens from this carbon, and 30% where the importation happens from the permanent carbon. So the same explanation for the region, right? Okay, here also an example, which is similar. Also, importation could happen on this carbon, or the Russian could happen on this carbon. So this carbon will be favorable because it's less substituted number of hydrogens. So they are kind of 70% or 33%. By the way, you saw this A or Z. What does it mean, A or Z? Cis and trans in alkenes. So E and Z, A means, what does it mean, E? Yeah, trans. And Z means they are cis. Okay? So why we get something like this? So we'll explain this one and we will go. And next week we have a quiz on the nucleophile substitution reaction, okay? Don't worry, the things that we explain will be in the exam, the test, and everything. And also I need to divide you into groups to do a presentation at the end of the semester. So there's no way, so you have to do it. So think about this. Why we are having cis and trans alkene as a product? Why? What's the problem with the cis and trans here? Okay? So I'm losing weight. That's good. That's good. Okay? What does it mean? Why we have cis and trans sometimes mixture of the product? So here it's supposed to get, a trans, for example, because it's antiperpolent. But why we have the cis sometimes? So here we could have two products. Let's say major and minor. A major is, let's say R2, let's say here, R. So this is trans. So this is what? A. Or we say trans. So E alkene, or we have the Z alkene. So we say Z, not Z. The correct Z. So we have the Z and the E. So when the trans state is actually antiperplanar, that means it is already E transition state because the base is in opposite, direction or opposite position to the leading group. So you will get trans or E. But that's not always, it's not easy to control it because that depends on the chemical environment on the substrate. If the substrate is crowded, is crowded around the nucleophile, the leaving group, if the leaving group here on a, very crowded molecule. So therefore, it's not easy to control the E transition state. So you will not get only E, you will get some kind of Z. So it's all about the structure here. If it's like this, opposite each other, then you get the E. But if it's like there, the other side, let's say base here. It's like this. So Some bases will be like this. So translator looks like this. So instead of taking, the proton from the opposite side, because when it comes from the opposite side, that means that proton will be, and the other side. So it comes from this side where they are, on the same side, the living room and here. So you will get the E, so you will get the Z, which is the cis. But if the base comes from this side, and then you get trans. So this is what called, this is the stereo, or is it called the stereospecificity? Okay, or stereochemistry, kind of stereochemistry, but it's not like fire. Just the configuration of the molecule. So put this in your hand and for the next lecture. So do we continue or we should stop? What time? We will see like, okay, we will finish next lecture. We'll finish the rest. The remaining is very simple.